Hey, it's Neil Smith here. Hope you're doing well. The following problem seems a bit overwhelming, but be patient with yourself. It's just adding, subtracting, looking some numbers up in tables, throw in a few nuances, a couple concepts to keep straight, and before you know it, you'll be doing these problems. They're not that bad. You got this. Determination of compass error by azimuth of the sun, practice problem 7. Here we are in problem 7. And let's get our givens. So first we're saying, what does the problem give us? It gives us the date. The date is January 26th. And it gives us our zone time, 1615. Zone time is equal to 1615. Gives us our DR position. Our DR position is equal to lat 27 degrees, 14.0 minutes south, and our longitude is given as 57 degrees, 22.0 minutes west. At that time, we observed the sun bearing 266. The sun bearing is equal to 266 degrees PSC. And the chronometer reads 8:13:19. So the chronometer reads 8 hours, 13 minutes, 19 seconds. 8 hours, 13 minutes, and 19 seconds. And then the chronometer error, so the chron error is equal to 1 minute 46 slow. 1 minute 46 seconds slow, and that means we add it. And the variation is given as 4 east. Variation is equal to 4 degrees east. The problem wants to know, what is the deviation of the standard magnetic compass? So deviation, it wants to know deviation. What is that equal to? So we'll start out, we'll get the approximate GMT to make sure we're in the right day. So the approximate GMT, make sure we're in the right day. So we'll take our zone time, which is 1615. Double check that. Yep. Zone time equal to 1615. And we'll take our longitude, which is equal to 57 degrees west, and divide that by 15 to get our zone time, or our time away from Greenwich Mean Time. 57 divided by 15 equals 3.8. 3.8, you round that up to the whole number, so 4 hours. And we need to figure out, is this 4 hours? Do we add it, subtract it? What do we do with that 4 hours? So we can say, if we are on the prime meridian, right? This is 000, it's Greenwich Mean Time. Here's some time zones. If we go to the east, we are adding. If we go to the west, we are subtracting. Imagine you are in New York, and what time is it in California? It's going to be less. We are in the west, so we need to get back to Greenwich, we need to add. So we're going to add this 4 hours right here. So back over here, we're adding 4 hours. That brings us 2015. So this is the approximate GMT. Cool. Now let's find the actual GMT. Actual GMT. So we take the chronometer time, 8:13:19. So let me just keep track of all this. Chron time is equal to 8 hours, 13 minutes, 19 seconds. And the chron error, it's slow, so we add it, and it's 1 minute 46 seconds. 1 minute 46 seconds. We can add these together. 9 and 6 is 15. 1, that's 1, 2, and 4, that's 65 seconds. 14 minutes, 8 hours. There's only 60 seconds in a minute, so we can take 60 from here and add it to the minutes. So now we're at 8 hours, 15 minutes, and 5 seconds. And if we look, this 8 hours, and this one's 20, our approximate, we do this so we know what day and time we're in, because it's possible to be in another time. This chronometer is kind of like an analog clock. So is it day or night, essentially? We add 12 hours, we get the other side of it. So if you add 12 hours to 8, then we get our 20 hours, 15 minutes, 5 seconds. Now we're lined up. 20 hours and 20 hours, 15. Okay, so this is our GMT, and we're in the same day, January 26th. Good. There's our GMT. 20 hours, 15:05. With that GMT, we can go ahead and find the Greenwich hour angle, or GHA. GHA, we find it in two parts. We start with 20, so the GHA of 20 hours, and then we find the GHA of the increments, which is 15 minutes, 5 seconds, 15 minutes, 5 seconds. And at the same time we look up this, our declination is essentially on the same line. So our declination and our decorrection. So declination and our decorrection. We'll get those at the same time. So we'll jump into the Nautical Almanac and find January 26th. It'll be at the front. July, May, April, February, January 28, 29, January 26th. And we need the sun column. And there's the days again, 25. We're 26, and we're 20 hours. So 26 down, 20 hours. There we are, this line. 116:49.8. So we'll record that, 116:49.8. Don't mess that up. There we go. 116:49.8. 116:49.8. And we'll get the declination and decorrection. So the declination's right next to it. If you look here, 26 for 20, that south drops down. South 18, 34.5. South 18, 34.5. South 18, 34.5. South 18, 34.5 degrees minutes. And we'll get our decorrection. The decorrection is right here at the bottom. It's 0.6. We need to know if we add or subtract that. So we come to the 26th for 20, and now here's our declination. If we move down to 21 hours, it's getting smaller as we go down. So we subtract that 0.6. So subtract 0.6. And in the next step, we'll get the correction for this. So let's jump into our increments. The GHA for 15.5. Increments is in the back of the book. 40, we're looking for 15 minutes. 19 minutes, 16, 15 minutes. So here's the minutes, right? And here's seconds. So we're 15 minutes, 5 seconds. 15 minutes, 5 seconds. And we're in the sun column. So 3, 46.3. 3, 46.3. We get 3, 46.3. Okay, and now we can go and get our D correction here. For 0.6, here's the D correction. 0.6, we use 0.2 right there. So we're going to subtract 0.2. Subtract 0.2 minutes. This will give us our total declination. So 5 minus 2 is 3. And that's 34, and south 18. This is our declination. Good. And now we can crunch these numbers and get our total GHA, or the GHA of the sun, rather. So I'm just going to punch it in. 49.8, 49.8 plus 46.3 equals 96.1. 96.1, and then this is 119. So I'm just going to leave this for now. It looks a little bit odd. You don't usually see 96 minutes, but we need to get our longitude going here. So our longitude is 57 degrees 22 west. If it's west, we subtract. So we're going to subtract our west longitude of 57.22, 57 degrees 22.0 minutes. Again, we're subtracting that. So 96.1 minus 22, 96.1 minus 22 equals 74.1, 74.1, and then 119 minus 57, 119 minus 57 equals 62. 62. And now I'm going to take 60 out of here and add it over here. So we get 63 degrees, 4.1 minutes. This is the local hour angle, or LHA, of the sun right here. Now we are ready to put these into our table. So we start out with declination, and then we need our DR latitude, and we need the LHA of the sun. We get all these values. So our declination, south 18, 34.3, south 18, 34.3, and our DR lat is 27, 14.0, 27, 14.0 minutes south. And our LHA is 63, 14.1. 63 degrees, 14.1 minutes. And so if we take a look, we need some information from here. Our declination and DR lat have the same name. They're both south. So dec and DR lat are the same. Good. That'll come in handy. We need to know that. And now we can get our base argument. So our base argument is just these degrees. So it's 1827.63. 1827.63. These are all degrees. That lines us up to get our base angle, or base Z, which we will get from the site reduction tables. Site reduction tables. And we are 63. Our LHA is up here on the top. So we're 63, and we're the same. You said they had the same name. So we got same on this side, contrary on this side. We need to be over here because we're same, and we're 63. And we're at 27. And we need the declination of 18. So if I line this up on 18 right across, now we're same, 63, 27 in the Z column down to 18, 84.7 is our base argument, 84.7. So now we're here, 84.7 degrees. This is our base all the way down. Now we can get our tabulated Z. Tab Z. And in order to get this, you just take your base argument, raise the declination by 1. So it's 1927.63. And then you raise and you record it here. Then you raise the DR lat by 1. So it's 1828.63. Record it here. And then finally you raise the LHA by 1. So it's 1827.64 and record it here. So let's do that. The declination's the fastest one to get. So bump it up to 19. So we just take this, bump it up to 19. And so now we're same, 63, 27 in the Z column, 19, 83.6. 83.6. And now we bump up the DR lat by 1. So make sure you get back to the 18 line. There we are. And now we're same, 6'3", 28. And we come down here, 85.3. 85.3. And now we bump up the LHA by 1, which means we'll have to turn a page to get to 64. And we're still at 18. So now we're same, 64, 27 in the Z column down to 18 declination, and 84.3. 84.3. Good. So now we can get the difference between the base and the tab, the difference in Z. And if we put this number into the calculator first and subtract this one, we'll make sure the sign is correct, like whether it's negative or positive. 83.6, 83.6 minus 84.7, 84.7 equals negative 1.1, negative 1.1, 85.3, 85.3 minus 84.7, 84.7 equals positive 0.6. Now last one, 84.3, 84.3 minus 84.7, 84.7 equals negative 0.4, negative 0.4. And our next column is going to be the increments. So we record our increments over here, which is just simply the minutes that we were dealing with over here. So 34.3, 34.3 minutes, 14.0, 0 minutes, and 14.1 minutes. Okay, and now we can find the correction. So the correction is equal to the difference times the increments, all divided by 60. So let's check those out. We'll crunch these. So it's going to be difference times increments divided by 60 for all three of these lines. So negative 1.1 times 34.3 equals, divided by 60 equals negative 0.63. Negative 0.63. And now 0.6 times 14, 0.6 times 14 equals, divided by 60 equals 0.14. And the last one, negative 0.4 times 14.1 equals, divided by 60 equals negative 0.9. Negative 0.09. I misspoke there. So the total correction is equal to the sum of all these. So negative 0.63 plus 0.14 minus 0.09 equals negative 0.58. Negative 0.58. We're gonna round this up to negative 0.6 is our correction. So with that correction, we come back here and we have our base z, which is equal to 84.7. 84.7. Now we have our correction, which is equal to negative 0.6 minus 0.6. This is going to give us our z, and it's going to be in quadrantal notation. So 7 minus 6 is 0.1. This remains 84. Now we need to name this thing, north or south in the front, east or west in the back. So we name the front same as dr lat, south. And then we say our LHA is less than 180, which makes it west. So now we need to get ZN, which is angle from north. So let's map this out a little. Okay, so we get north, south, east, and west. And first we're south, so we're this way. We're from south, and we go west 84 degrees. So we're right over here somewhere. This is our Z. And we need ZN, which is from north. So this angle is 180, and we have to add that to Z. So our ZN is equal to 180 plus Z. So to get ZN, it's 180 plus 84.1, and that is equal to 180 plus 84.1 equals 264.1. 264.1 degrees. Now we can correct our compass. We can say true TVMDC, true variation magnetic deviation compass. If we go from true to compass, we add west, And so our true is 264.1, 264.1 degrees true. And our variation was given 4 east, 4.0 east. We're going down, we subtract that, so you get 260.1. And our compass was given of the sun 266. So it's 266.0 degrees PSC. We do this. So to get from 60 to 66, we need to add. So we know this is going to be west. So 266 minus 260.1 equals 5.9. 5.9, we say west. So let's check out our answers. There it is, C. 5.9 west is the answer to determination of compass error by azimuth of the sun, practice problem 7.